Okay. That's loud. All right. I can't seem to change the volume down here, so I'll either have to talk really quietly or hope they can fix it in the back. If I get carried away and you all get like blasted into the back of your seats, I apologize in advance. It's easy to get carried away because we're talking about Bayes nets again today. Okay. All right, so today we're going to talk about inference in Bayes nets, which is the process of taking your lovely Bayes net that describes your domain and your variables and the probabilistic interactions between those variables locally and answering global questions like, what does this variable over here do if I observe something clear on the other side of the network? So let's first remember what Bayes nets actually are. Because we're going to be using this semantic definition formula over and over again today and in the next lecture. So a Bayes net they're also called graphical models. They're a model of your domain. The nodes in the Bayes net represent variables that you care about in your domain, and those variables have values, which are the domains of those variables. The network is also a directed acyclic graph over those variables, where the arrows encode something about direct influence between variables. And in particular, underneath each variable in the network lives a conditional probability table that specifies what that variable does, meaning what is its conditional distribution over all of its values in its domain, given the various settings of the parent. And that's where we get to say, actually, let's just pull up an example. Okay, so from a couple lectures ago, we had built this tiny little Bayes net, and it's still there. And in this Bayes net, each node represents a variable, like low pressure causes rain, rain causes the drip in my roof, and it also causes traffic. There's no arc between drip and traffic because there's no direct influence between them in a way that we mostly made precise in the last lecture when we talked about conditional independence. But if we take a look inside here, inside each of these, so underneath low pressure, it doesn't have any parents. There's just a little probability over that variable that says, oh, there's low pressure 10% of the time. But if I go to a more interesting node, like traffic, there is a description of how likely traffic is under all its conditions. So here it says when there's rain, 80% chance of traffic. When there's no rain, 30% chance of traffic. And in general, the more parents you have, the more different behaviors can exist at that node because you get to specify a conditional probability for each setting of the parents. So maybe we'll actually go look at that. Let's say we want traffic to also depend on I guess before we had a ball game. So there can be a ball game or not. And I'm going to make an arc between ball game and traffic. And now what I have to do is suddenly this sort of becomes a pain because I need to specify how likely traffic is for each combination of the parents. So maybe if there's rain and ball game, almost guaranteed traffic. If there's rain but no ball game, 80%. Ball game but no rain, maybe that's 50%. And neither rain nor ball game, maybe that's 20%. And so the more parents you have, the more action there is inside that node because you've got to specify what it does for each combination of the parents. So that's written here. Underneath each node X is the following conditional probability family. It's a distribution over X, but it's not one distribution over X. It's a distribution over X for each combination of values of the parents. A Bayes net, which is this graphical structure along with a conditional probability family for each node, encodes a joint distribution as a product of local distributions. So if your nodes in your network are x1 through xn, here is the definition of the joint probability your Bayes net encodes. The joint probability of some complete assignment x1 through xn is the product of each xi given the parents in the network. If you have no parents, that's a bunch of independent probabilities. That would be a very simple network. If nodes have all kinds of parents, then this starts to become a complex expression, and in the limit this will look like the chain rule, and it will represent an arbitrary class of probability distributions. In general, you want to build a network that has all of your variables connected up, but with a small number of parents for each, so that each of these terms is relatively simple, even though the whole network it defines may be encoding all kinds of interesting interactions. All right, so this is the definition of the probability of an entry in the joint probability table defined by a Bayes net, and you just multiply together all of the appropriate conditional probabilities that match on those values. Sometimes I'll call this the Bayes net reconstitution formula, because it lets you take these little conditional probabilities and inflate them into a giant joint distribution where each and every entry in that high dimensional table gets filled in according to this recipe. Sort of a wasteful thing to do, but we're going to have to do it for a while until we have a better algorithm, which we'll get today. Okay. Here's an example of a Bayes net. Hopefully, this network is not only familiar, you're getting mildly sick of it. This is the alarm network. It's a classic. This one says, burglaries happen, but rarely. It's up here. There's no parents to burglary, so it's just a little marginal distribution over that. Earthquakes happen, but rarely. That also doesn't have any parents, so just a marginal distribution. The heart of this network lives under the alarm node, which specifies how likely it is that alarm is going to go off when there's a burglary and an earthquake, when there's a burglary but not an earthquake, and so on. And so, for example, if there's a burglary and an earthquake, the alarm goes off 95% of the time. Okay. Similarly, John has a node and Mary has a node that specify how often they call with and without the alarm. If I started adding parents to these things, like maybe Mary always calls me when there's an earthquake, then suddenly Mary's distribution family is going to be more complicated because now I have to specify what she does with and without earthquake, with and without alarm, and all the different combinations. Okay? So this is what's in the Bayes net, and it defines any entry in the joint distribution over these variables B, E, A, J, and M. So for example, if I come up to you and I say, all right, you've got this Bayes net, which is a bunch of little local pieces, but I'm intensely curious how likely it is that there is a burglary, but not an earthquake, the alarm goes off, John does not call, but Mary does. That's this event here. And now you're thinking, that's an awfully specific event. But remember, all the things we actually care about, like how likely is it that there's an earthquake if Mary calls me, are derived by summing together and dividing lots of these elementary events. Okay, so if I really am intensely curious about this, I look around and I see, you know what, my Bayes net doesn't actually list an entry for that element of the joint distribution, but it gives me a recipe to reconstitute it. So I can multiply together the relevant pieces. Let's see. So we need the probability of a burglary. All right, minus E, an earthquake. And now I need to know the alarm is plus A. Well, but it's plus A in an environment where it's plus B and minus E. So I go find that here. So that's plus B minus E plus A. That's here. Okay, and I look up all the relevant things. So John does not call despite the alarm 10% of the time. Mary does call when there's an alarm 70% of the time. And I can multiply these little pieces together, and I'll get some number. I don't know what that is. Some small number that represents that exact event. And if you say, well, actually, I just want to know how likely it is Mary calls. Well, how do you find that? You take this event and a whole bunch of other events where Mary calls, and you add them up. Which events? All the events that are plus M, and then you sum together everything on all the other axes in all combinations. And that gives you the total marginal probability of Mary calling. And in this Bayes net, you can answer questions of the whole distribution by assembling it as you go from the Bayes net definition. So if I told you, I've changed my mind, I'm intensely curious about no burglary, no earthquake, the alarm goes off anyway, but nobody calls me. You could go and you'd be like, all right, I'll circle different entries and I'll multiply them together, and I can get you that probability too. And whatever probability I ask for, you can fetch it on demand, even though you're taking entries, you're fetching probabilities from a high dimensional table of exponential size, but you're building it out of local little pieces of basically linear size, assuming all of the conditional probabilities are of constant size. Okay. All right, so what do we have with Bayes net so far? We've seen representation, which is What probability distribution does a Bayes net represent? We've talked about conditional independence. What conditional independences hold for sure in a network based on the structure? And you saw last time how we can do a kind of a search operation and look at various kinds of paths in the network to detect independence. Today what we're going to talk about is probabilistic inference, and we actually already spoiled this lecture a little bit 2 lectures ago when we talked about inference by enumeration. Unfortunately, that's usually intractable, so we're going to replace it with a much better algorithm today, which is also intractable because this is an AI class and everything we do is NP hard, but it's usually better. All right, so we're going to talk about inference by enumeration again. We're going to talk about variable elimination, which is usually much better, even in the worst case, it's just as bad. We're going to talk about why these things are so hard, and in particular, why is inference in a Bayes net NP hard. And then we'll talk about sampling, but not today. And then finally, learning these networks from data will come later. All right. Any questions before we start in on inference? Okay, let's do it. So what is inference? Inference means a lot of different things to a lot of different people. Here in this class, it means calculating some quantity from a joint probability distribution. So you imagine the given is some collection of probabilities. Maybe it's the whole joint probability table in all its exponential size glory. More often, it's a bunch of conditional probabilities that define a Bayes net. Okay, some examples of things you might calculate from those givens are the canonical thing is a posterior probability. I care about variable Q. There's a bunch of evidence variables whose values I know. And unfortunately, there's going to be a bunch of other variables called hidden variables that I don't care about and I also don't observe, and we're going to have to sum them out, and that creates a lot of the time complexity. So posterior probability is give me a distribution over Q given the evidence I have. Another classic canonical query you might do is a most likely explanation query, where you say, I have some evidence. I would like to know the most likely value of one or more variables given that evidence. We're only going to talk about the top kinds of queries today, but the bottom ones are solved in basically the same way. In most cases, the changes are limited to sums turning into maxes. Okay. All right, so let's figure out how to answer mainly. Let's get back on track. Let's wait. All right. So, posterior probability queries. We had this algorithm called inference by enumeration. It barely fits on the slide, so let's go through it again. But in fact, it's really simple. It's just really, really excruciatingly slow in practice. So the general case is we have a Bayes net. So what's our Bayes net look like? It's got a bunch of circles, and those all represent some variables. And there's one that we care about. Let's call it Q, right there. You care about that variable. Actually, often the variable you care about is at the top. Then there's some things we know, like maybe we know the value of this variable, and the value of this variable, and the value of this variable, and the value of this variable. And of course, the whole reason that this is interesting is because we've also got all kinds of arrows going between these variables in various patterns. Okay? So there's your Bayes net. You have a query variable that you care about. That's your query variable. We have evidence variables, which are, I know that variable takes on the value 7. And then there's the bane of your existence. There are the hidden variables. There are these variables and these variables and these variables. There are all those variables in your network that at the moment you don't observe, and you also don't care about their values. So if I give you a joint distribution and I say, hey, here's the probability distribution over x and y, I'd like to know the probability that x takes on the value big. What do? You say, well, that's not in my network. That's not in my joint distribution, but I'll find all the entries that say big, and I'll add them up, and that will give you your marginal. Okay? So we talked about that. We've had that for a while. In this case, x is the query variable, y is the hidden variable, because we have to get rid of it by adding it out, by summing it out. And there are no, in that case, evidence variables. Okay? So we have evidence, query, and hidden. That's all your variables. And we'd like to have the probability of Q, the query variable, given all the evidence variables. So what do? Let me make it go away. If I give you the whole big joint distribution in all of its exponential size glory, step 1 is you take the entries consistent with the evidence. So everything that doesn't match your evidence, you just delete it from your table, and your table shrinks. Right? So all those entries that don't match the evidence, they're gone. You have a smaller table. Your table is a big joint distribution, so it used to add up to 1. right? Because it's a happy, well-formed distribution. As soon as I knock out all the rows that don't match the evidence, it doesn't sum up to 1 anymore. What does it sum up to? So if I was like, stop doing inference, add everything up. Let's say my evidence was E. What does this add up to? Any guesses? It's not 1 anymore, it's smaller because I knocked out all the rows that said something other than E. Like this was maybe like, I know it's sunny, knock out all the rainy rows, knock out all the windy rows or whatever else is in there. Okay? What's left is all the rows that say sunny. And when you add them up, you get the probability of sunny. So this thing is going to be the probability of your evidence. It's like this magic space I can't actually draw an E in. Okay, so that's the probability of your evidence. But we're not going to do that. That's not why we're here. We didn't come for the probability of the evidence. So we're going to knock out the rows consistent with the evidence, and then we're going to sum out all of the variables we don't care about. That means take this still large dimensional table and get rid of dimensions of that array that correspond to variables that we don't currently want. And what we'll end up with is a tiny little... So in mathematics, that's this. So we have the whole distribution here. We're going to sum out the hidden variables. And so all those rows that differ only in their value of the hidden variables are going to collide and get summed together into the smaller array. And the smaller array represents the probability of Q and the evidence. And for each value of Q, you're going to have a separate entry. So what's this thing look like? It's now a one-dimensional array. And the difference between each entry in that array is they have different values of Q. Do they add up? Is it a distribution over Q? It's not. They still add up to P of E. But if you normalize it, which is the last step, meaning you add up all the entries and then you multiply them all by 1 over that number so that they are proportional to their values, but now sum to 1, you're going to now get, if you take this and normalize, you end up with P of Q, comma, all the E's, and you divide that by what we know to be P of E, you'll end up with P of Q given all your evidence. And that was the query you wanted. So that is inference by enumeration. You take your whole table, you select the evidence matching rows, you sum out the variables you don't want. We'll see that more in a second. You normalize and you're done. Okay, problems with that algorithm, aside from the fact that it barely fits on the slide. One, we don't have the giant joint distribution. We've got a Bayes net. And while we could in principle build the giant joint distribution, that would be a waste of space and time. So that's basically enough problems. We'll stop there. Okay. Let's get some more intuition about why this is a bad idea so that we can come up with an idea that algorithm that's a better idea. So, if you have unlimited time and unlimited space, inference in Bayes nets is easy. You take your Bayes net and you get your query. And so maybe somebody comes along and says something a lot more reasonable, which is, I'd like to know how likely it is there's a burglary given that John and Mary have called me. Okay, this is a reasonable query. It's not in your Bayes net. Your Bayes net tells you things like probability that Mary calls given the alarm. This is a case, by the way, side comment, of we've observed variables at the bottom, which is very common, right? This sort of, these, to the extent these Bayes nets represent causal domains, the stuff at the top sort of causes the stuff in the middle that causes the stuff in the bottom. You tend to observe the effects at the bottom and try to reason about the causes. It's not the only thing you can do with a Bayes net, but it's a pretty common thing that people do. We shade nodes to indicate that they're observed. So in this case, I've observed the values for J and M, they're both positive, and I'd like to know the value, or in this case, the distribution over B. What about E and A? I wish they weren't in my network. What can I do about it? Nothing. I got to work around it. You say, why didn't you give me a network that doesn't have E and A? Two reasons. One, maybe next time you're going to want E and not B, and you want this network to be sort of multi-purpose. And the second thing is, if you start deleting nodes from your network, the nodes that are left end up all pointing to each other in all kinds of crazy ways. Because simple interactions that were mediated by those hidden variables are now just sort of like a free-for-all of direct interactions between the remaining ones. So usually, you're going to have some hidden variables for one reason or another. So you're in this situation. I'd like to know the probability of B, the distribution over B, so that's going to be two values, one for plus and one for minus. Given J and M are both true, let's figure it out. We've got laws of probability. First law of probability says that conditional distribution over B is proportional to the values where we have joint distributions instead of conditional. So let's stop and figure out what this little fish shape with a B means. This is proportionality with respect to B. So this says these two things are almost equal. They're not actually equal. But they'd be equal if we summed up the values over B, and multiplied by the inverse. So that means they're proportional. Okay? And so what this says is if you want a conditional probability, you compute the equivalent joint probability and then normalize. All right, we know how to normalize. If I gave you this, so what is this? Like, what is this? I don't know, but it's something that says B, it says plus, minus, 0.2, 0.1, and when you normalize, you get 1/3 and 2/3. Okay? So let's compute this. Let's compute this joint value here. So what is that? That is for each value of B. I don't actually know that joint distribution, those joint probabilities either, but if I introduce E and A with specific values, suddenly the network tells me how to get these. So I want those joint probability entries. I now have to look for the probability of B and E and A and plus J and plus M. We're going to do it for each value of E and A, and we're going to have to sum them, okay, because those are variables we introduced. That's how marginalization works. And this capital letter means we're going to keep a vector around. That means we're going to be doing sort of vector math. We're going to be doing this exact same computation once for plus B and once for minus B. In general, we're going to be doing the exact same computation for every value in the domain. So when you see capital letters involved in these, it means vector math. Okay? It means that same operation is happening for each value in the domain. All right, so conditional quantity I wanted, joint quantity I wanted. This is a full entry from the joint distribution, which in principle the Bayesnet gives me. This is the rewriting of that according to the Bayesnet reconstitution formula. This is the chain rule as it applies to this Bayesnet. So it's not the full chain rule, it's just the multiplying together of the conditional probabilities of this Bayesnet. All right. What's that? That bottoms out in taking a whole bunch of individual probabilities and multiplying them together in a bunch of ways and adding them. Don't stare at that too hard, or your eyes will roll out of your head. Okay, get the idea? All right, great. So we have our algorithm. Here's why we don't use that algorithm. Here's a, by modern standards, what's the technical term? Extremely tiny network. But even in this network, if I wanted to know something like, hey, what is the probability that you have, I don't know, an extra car given here's your driving history and your age? Okay? I observe 2 variables. Great. I'm interested in 1 variable. Great. And the other 24 or whatever are hidden variables. So when I do that same formula, I'll be like, oh, I'm computing probabilities of, what is it, extra car given, some particular value of the age and some particular value of the driving history. And I don't know that, so I'm going to get the joint probability instead of E and H and A. But I don't know that, but I know how to do that. It's going to be a sum over, the whole rest of the network, P of E, H, A, lots of things. Okay. And so, because we're summing over lots of things, this is going to be an exponential time thing, and we can just go get lunch while it runs. Okay? So, already in this tiny, tiny network, it's bad news to do this in an exhaustive way. All right, so why is this so slow? The reason it's so slow is somebody was nice enough to give you this conceptually giant network in tiny little pieces. Right? So these tiny little pieces multiplied together define this exponentially large thing. And they have this warning on them, which is do not multiply us together to form the exponentially large thing. So what did we do? Step 1. Multiply them together to form the exponentially large thing. And then once we get the whole thing, what's the first thing we do? We collapse out all of those dimensions we don't care about till it gets small again. Maybe we should not inflate the whole thing before we start deflating it. And so what variable elimination is going to be is instead of joining up the whole joint distribution and then summing things out, we're just going to interleave those things. So we're going to join some variable and then immediately sum it out and then join the next variable and sum that out. And so we control that growth. And you say, why does that really matter if you're going to do 10 joins and then 10 sums? Why does it work to interleave them? The reason it's good to interleave them is because when we let that network grow, it grows exponentially. So if you join 10 times, things are growing sort of exponentially, and then by the time you sum them out, it's sort of too late. Whereas if we catch those joins early and sum out hidden variables as soon as we legally can according to the laws of probability and the conditional independence assumptions we have available, then we can avoid that exponential blowup. Okay, so we're going to interleave joining and marginalizing things. This This is called variable elimination. It's still NP hard, but it's usually much, much faster. And for certain kinds of graph structures, it's in fact efficient and sometimes even polynomial. All right, so we need some notation. The notation we're about to get is what are called factors. You've already seen the basic types, but there's sort of a whole zoo. There's like a menagerie. There's simple factors like joint probabilities and conditional probabilities. And then there's the weird stuff. I'm not even going to show you all the weird stuff. When this algorithm runs, it's taking little pieces of network and multiplying them together and summing out variables. And what you're left with is often some like weird hybrid of a joint probability and a conditional probability. Let's take a look at what you can get and build up some intuition. But just know that if you do this on a big network, the intermediate stages can be hard to think about. All right, so the factor zoo. Let's see what's in our factor zoo. There's the relatively innocuous stuff, like you know what a joint distribution is. What is P of x and y? Well, it looks like this. It contains a probability for each value of x and y. When you sum it up, it sums to 1 because it is a joint distribution over those two variables. And it's just a sort of enumeration of all of the cross product of their domains. Okay, so in this case, what's the probability of hot and sun? It's 0.4. Great, we know about joint distributions. Often, we are selecting rows of a joint distribution. Like, for example, somebody tells you, oh, hey, it's sunny. And so I might say, all right, it's sunny. Let's knock out all the rows that do not correspond to sunny. Once I've knocked out rows, I structurally still I semantically have the same thing. I still have entries of a joint distribution. They didn't like become a conditional probability or anything, but the dimensionality got reduced, right? Because on that one axis, in this case, that axis of sun, it's no longer all values. It's just the one. Okay, this is called a selected joint. You can think of it as a slice of a joint distribution. There's still probabilities of x comma y, but now x is fixed and y still ranges. This doesn't sum to 1. So if I look over here and I sum these things together, it's going to sum to probability of sun. Okay? So it's going to sum to the probability of what you selected. So there's probability of cold, comma, W. You knock out everything that doesn't correspond to cold, and you're left with a slice of the joint distribution. Okay, this is actually an important point to stop and think about the difference between what the numbers mean, right? These are still joint probabilities over T and W. 0.2 is still the joint probability of cold and sun. But as a data structure, it went from being a two-dimensional array to a one-dimensional array because I picked a value for one of those dimensions. How do I know what this is as an array, as a data structure? Capital letters indicate dimensions of the array. So T comma W in caps is a two-dimensional object, like what's shown here. Cold comma W, where there's only one capital random variable whose value has not been fixed, that's now a one-dimensional object. And if I go to cold comma sun, it's still a joint probability, but now it's a one-dimensional object as a scalar. Okay? That's important. We can reduce the size of the data structure without changing the semantics of what's in it. Okay? You want to know what changes the semantics of what's in it from a conditional probability to a joint probability? That's the laws of probability. You multiply things together and you cross things off according to the product rule or the chain rule. Okay? All right. Number of capitals is dimensionality of the table. All right. Here is a relatively harmless thing from our zoo that you've seen before. This is a conditional probability. This is the conditional probability distribution over y. See, y is a capital. So as a data structure, this is a vector over all the values of y. This is the probability of y taking on its various values given the evidence x. Each entry in this is a conditional probability of y given x. They all have the same x, but they have different y. If I sum this up, what am I going to get? Well, it's a distribution over y. If I sum up all the values, it's going to sum to 1. It is a probability distribution over y for the condition x takes on some particular value. All right. That's great. We know about conditional distributions. They look something like this. This is the distribution over W given T is cold. And so there's a value for each element in the domain of W here, and these things sum to 1. All right. You can also get a family of conditionals. This isn't too weird, but it's a little weird. This is distributions over y, but it's one for every value of x. So it's like you've taken P of y given this x and P of y given that x, and you've glued them together. It's a two-dimensional data structure. It's got a value for every value of x and every value for y, and everything in there is P of y given x for some x and some y. If you add them up, each little distribution over y adds up to 1, and there are x many of them, so this whole thing together now sums to more than 1. That's weird. Okay. So we'll look at them through the glass. It's getting a little weird. Here's what it looks like when you see probability of, say, w given t. You look at it, it looks two-dimensional just like w comma t, but if you peek a little closer, you'll see that for each fixed value of t, like these ones, we get a distribution over w. Here's another distribution over w. They've just been bolted together. It's a two-dimensional object. It's got variables for w and t. All right. Now we get to the weird stuff. Okay, you'll end up things like specified families. What does it mean when I hand you something and I say, oh, what's in here is the probability of a fixed value of lowercase y, like the probability of rain, and then it's given capital X. That means there's going to be an entry for every value of capital X. So this is a whole bunch of probability of rains, for example. So here's an example. This is probability of rain when it's hot. This is probability of rain when it's cold. What happens when you sum them up? It's not a distribution over rain and sun. It's a bunch of probabilities of rains. And so when you add them up, you get to, no one knows. They could be all 0, they could be all 1. Just depends on what those conditional probabilities are. This is no longer a distribution. It's no longer a family of distributions. It is a one-dimensional array because there's an entry for every value of x. But each of those entries is the conditional probability of some particular value of y, which is usually an evidence value. Okay? So that's weird. You'll see those too. Okay? How do we get these things? We get these things because somebody hands us little pieces of Bayes-net. We're going to be selecting the value of the evidence wherever it is on the conditioning bar. It could be on the left or the right. And then we're going to start multiplying things together. So we're going to get all kinds of stuff. Okay? Any questions? All right. So, in general, we're going to be writing things that look like this. We're going to be writing conditional probabilities of some number of variables. Possibly 0. It's not going to happen today. Don't let it freak you out. Given some number of other variables. Possibly 0. That happens all the time. Those are marginal probabilities. This is what's called a factor. It's always going to be data structure-wise a multidimensional array, where every capital letter is going to indicate a dimension of the array, and we're going to have the whole cross product of all of those entries. The values in this factor are always going to be specific values of probabilities of the stuff to the left of the conditioning bar, given the evidence to the right. Anything that's assigned, meaning we write it with lowercase, is a dimension that's missing or selected from this array. So we're going to have all kinds of factors, and we're going to generate them sort of algebraically as we go. Okay? All right. Let's do a specific example now that we have our factor zoo. So this is a tiny example. This example is so small that it's actually fine to just build out the full joint distribution, but we'll resist. So the random variables are, is it raining or not? Boolean random variable. T, is there traffic or not? Boolean random variable. L, am I late for class or not? Which I nearly was today. Boolean variable. Okay, what's living in my Bayes-net? Well, I have P of R because it doesn't have any parents, and it says 10% of the time it rains. Okay. What's under T? This encodes the probability of traffic given yes rain and given no rain. So in fact, this is a family of conditional distributions. I eyeball it, I see it adds up to 2 because there are in fact 2 distributions over T, one for plus R, one for minus R. You can see it's a 2-dimensional data structure. They're all conditional probabilities of T given R. Same thing under L. There's a bunch of conditional probabilities given the parents. Okay. Here's distribution over L given plus T, given minus T. Okay. Let's say somebody comes to me and said, I'm intensely interested in the probability distribution over L. That is, forget this raining and stuff. How often are you late for class? And I say, well, that's annoying, because if you had asked me how often it rains, I have that answer at my fingertips. This answer, P of L, I need to compute from what I know. It's not just sitting in there. I can tell you probability I'm late when there's traffic. But in order to tell you the overall probability, I sort of need to know how often traffic is, but I don't have that either, so I need to sort of combine that with rain, and that's what the Bayes-net mathematics lets you do. So I could look at this and I could be like, well, because this is just a distribution over these variables, I can always write this. This is introducing a variable and summing it out. The probability distribution over L is just the sum over all the values of R and T of the probability distribution over R, T, and L. Okay, I just introduced some variables, but I'm collapsing them out. So that's law of marginalization here. Now, I don't actually know that either.
That's an entry of the joint, but because it's a Bayes net, I can break that down into a product of things I do know. I do know P of R, because it's sitting there under R. And I do know T given R, it's sitting there under T, and I do know L given T. Okay? All right. So, inference by enumeration, which you already know. We're going to see it again through the lens of factors, which will let us get to variable elimination. All right, we're going to track these factors from our zoo. The initial factors, the givens, are going to be conditional probability tables. Okay? You get one per node. And if I have some node sitting here in my network that's called A, and it's got a parent called B and another parent called C, my initial factors are going to look like P of A given B and C. Okay? So the network structure gives me my initial factors. And so for the computation of P of L in that little lateness network, these are my initial factors. You say that's just the Bayes net. That is just the Bayes net. Okay. All right. Step one, just like our original inference by enumeration, we have to select values that match the evidence. So let's say we're going to do a query, and I'm going to say something like, maybe, what's the probability that it's raining given that I am late? Well, if we know L is plus L, then the initial factors are going to be smaller. P of R doesn't change because it's all sort of valid for plus L and minus L. But all the entries that actually mention L in them get pared down to just the amount that is consistent. Now, conceptually, I had this whole giant joint distribution, and conceptually, I just knocked out half the rows. I knocked out all of the minus L rows. But to my Bayes net, I sort of knocked them out locally. But the consequences is if I inflated the whole thing, half of the network would be gone now. Okay? All right. So, inference by enumeration. Initial factors are local conditional probability tables, one per node. Any known values are selected. That's your evidence. Join all your factors, whatever that means. Eliminate all your hidden variables. We know what that means. It means sum them out. And then normalize what's left over. Okay? So, operation one. What does it mean to join factors? I've got all these little pieces, so I've got factors, and I need to merge them together. But I don't just want to multiply everything together. That would give me the whole Bayes net. So we need an operation for joining a selected set of factors. It's sort of just like a database join. Okay, so in a database join, you've got some table, and it sort of talks about A and B. And then you've got some other table that talks about A and C, and you join them together. And what do you have now? And you've got this big table that talks about A and B and C, except now it's big. I guess it depends what join you do. Okay, so this is like a database join. And what happens when we join? We talk about joining factors. In particular, we talk about joining on a variable. So maybe we'll join on a variable X. We get all the factors that mention that variable. If you leave one out, weird things will happen. Don't do it. So if somebody says join the factors on X, I summon to me all of the factors that mention X. Some will mention it on the condition side of the bar, and exactly one will mention it on the left-hand side of the bar. And that's whatever was living under X to begin with. So we summon all the factors that mention our magic variable. We build a new factor over the union of the variables involved. So let's do an example of that. Let's say I would like to take my little R, T, and L Bayes net over raining, traffic, and lateness, and I want to join on the variable R. Step one, I gather all of the variables that mention R. What mentions R? P of R. Great. And P of T given R. And if R had other children, they would mention R too, and we'd summon them too. But at the moment, we just get these two. What does it mean to join? It means we create a new array that's going to represent the product of these things, whose dimensionality is the union of all these variables. So in this case, the union isn't actually any bigger. And we'll end up with R and T. And because we multiplied a P of T given R with a P of R, I know from the product rule that's going to be P of R comma T. I don't have to know that to join variables. This is a mechanical operation. But because I'm tracking what these things mean, and I know the laws of probability, I can infer that what's actually going to live here is going to be P of R comma T. But I can do the algorithm anyway without giving it a name. So what do I do? For each entry of this new thing, which is still a two-dimensional array, it looks just like this one, only the numbers are going to be different. For each element, I'm going to do a pointwise product. So for example, in order to get the entry for minus R plus T, I'm going to get minus R plus T. I select everything that's relevant, and I multiply them together. And I do that for every entry. It's a pointwise product. All right, that's what joining on a variable means. We grab all of the factors that mention the variable. I create a possibly higher dimensional array to hold all of those variables, one per axis, and then I do a pointwise product of everything relevant. Once I've done that, I sort of don't have a Bayes net with an R pointing to a T. I've sort of merged them together into one mega variable called R comma T. We've never seen that in our network, and we actually won't, except in this lecture I'll draw that to evoke the fact that R and T have sort of been conflated by this joining process. Okay. All right, let's do an example of multiple joins, where we take all these little pieces and we stick them together and get something higher dimensional. Okay. All right, so here is that network. P of R. Raining causes traffic. Traffic causes lateness. Here are the local probabilities involved. Let's go crazy joining things up. So I can join on R. What's going to happen? I'm going to gather everything that mentions R. That's P of R and P of T given R. I'm going to get something that multiplies them together. So it's going to be something with T and R, because that's the union of the variables. And we know it's going to be T comma R, because if you multiply a conditional by a marginal, the product rule here says you're going to get a joint probability. So we already did that. We're still going to have this other factor. It is unchanged. It is not harmed in the joining of R. But there's this new factor, R comma T, that we saw before that we got on the last slide. I've taken one step away from the Bayes net and towards the joint distribution by collapsing together R and T. So let's go crazy. Let's join on T now. All right. So if I join on T, I gather everything that mentions T. And look, everything mentions T. When I do this, I'm going to get a new factor. It's going to be a probability of something. It's going to have dimensions for R and T and L. And I know by sort of the chain rule here and what I'm multiplying together that in fact what I'm going to end up with is the probability of R and T and L. All right, what's it going to look like? It's going to be a three-dimensional array here, one for every value of R, every value of T, and every value of L. And for each element here, like if I want plus R plus T minus L, I grab plus R plus T from here and plus T minus L from here, and I multiply them together. So again, it's a pointwise product, and now we've made something bigger. And in general, if you go crazy joining stuff together, these tables get higher dimensional, and as you add dimensions, things grow exponentially fast. Okay, which hopefully I've said enough times is not what we want. Okay. All right, so that's multiple joins. If you just go crazy and start joining on variables and pressing the join button like a maniac, you're going to end up with a full joint distribution, and it's going to be big. Okay. So how do we control this growth? We have something that basically doubles the size of things by joining them, or perhaps much worse. We also have an operation which halves the size of things by eliminating a variable. This takes a larger dimensional object and deletes one of the axes by collapsing everything on that axis and summing them together. So this is called marginalization. It's just like marginalizing from before. It takes a factor and sums out a variable. So a factor becomes a smaller factor. This is a projection operation. So for example, if I have my factor over R and T, this is also just a joint distribution over R and T, and I want to get rid of a factor, I say, you know what? I don't care about R. I just want to know the probability of traffic. And I say, unfortunately, my network mentions it. I'd like my network to not mention it. So I sort of I can't just scribble it out, right? Because then there's going to be a bunch of T's that collapse and a bunch of R's that collapse. But if I scribbled it out, I would say, I guess I got to put together those two plus T's. And I guess I got to put together the two minus T's that have now collapsed. And if you do that, you'll end up with a distribution over T, and it'll look like that. So this two-dimensional thing became a one-dimensional thing, and where there was collapsing, I added things together. That's marginalization. And this is the thing that reduces the size of the objects that we're constructing. So in general, we're going to join, and then as soon as possible, we're going to marginalize everything we don't need that's legal to marginalize so that we can keep things small and controlled. Okay, so here's an example of multiple elimination. Here's a joint distribution over R, T, and L. It's a three-dimensional object. It's a joint distribution over three variables. Where did it come from? We reconstituted it from a Bayes net, but for the present purposes, it doesn't matter where it came from. Okay? What can I do to this thing? Well, I can answer questions like, hey, what's plus R plus T plus L? Okay, it's 0.024, great. I can also start projecting things out. So I could sum out R. That basically means I get rid of this axis, and all the plus t plus l's that collapse get added together. And now I have something that's just two-dimensional, t and l. Each one of these entries is backed by a whole bunch of things that also say plus t plus l, but used to vary over r and have now been collapsed. All right, that was summing out r. Okay, we're gonna pare it down. It's gonna be brutal. We're gonna sum out over t. What's left? Just gonna have p of l left. That's just a plus L and a minus L. And there you have it. My probability of lateness is 13.4%. In this model, hopefully real statistics do not bear that out. Okay, so we can join a bunch of things. We'll get in the limit, we'll get the whole joint distribution. We can sum out things from the joint distribution. In the limit, we'll end up with just like one variable left. And it turns out that that's all you need to do inference by enumeration. Somebody gives you your conditional probabilities in your Bayes net, you select your evidence, you join until you can join no more, and then you eliminate everything you don't care about, and then you normalize. That's it. And all variable elimination is going to do is interleave those operations. Okay, so variable elimination, and then we'll take our break for today. Variable elimination is simply marginalizing early, and you say, I have a really good idea. I'm going to marginalize everything at the beginning, just like project it all out. The problem is when you can't actually marginalize things until there is only one factor that mentions them. So if you sit down to your Bayes net and you see, oh, I've got like a P of A, and then I've got a P of B given A, and you're like, I'm going to marginalize out A. Okay, don't get too excited. You can't marginalize that out yet because you haven't yet done the joining that's necessary to connect everything that A mediates. So here A influences B. You would have to join these together before you could marginalize it. If you had P of C given given B and A, let's say, as well, you would have to join all of these on A before you could marginalize on A. And so the rule is you can't actually marginalize something unless you only have one factor that has it, that represents the distribution over that variable, perhaps jointly with other things and under some condition. So the basic recipe is going to be simple. You can't marginalize it until you've joined all the factors that have it. So you're going to pick a variable, you're going to join on that variable, and you're going to immediately marginalize on it. You say, what about my query variable? I don't want to marginalize over that. Okay, don't pick that one. Leave that one for last. What about my evidence variables? I don't want to marginalize over them. Well, the first thing you do is select them, so they're basically gone in a data structure sense. So let's take a look in the traffic domain and see what this is going to look like. P of L. Okay, we're not going to actually go through P of L again. We've already done a couple times. But just sort of eyeball this is another look of sort of what variable elimination is. Eyeball the inference by enumeration. It says, oh, you want P of L? Well, too bad. We don't have that. Instead, we have P of sort of L, comma, T, comma, R, which decomposes into this product because it's a Bayes net. So we're going to write that product, and then we're going to do lots of summing. The summing is all out here, and this represents joining those factors on R, joining the factors that remain on T, then eliminating R, then eliminating T. All variable elimination is going to do is move the sum in. So you're going to join on R, but then immediately eliminate it. And what's going to be sitting there after you do that is a little P of T factor. And now you can join on T and eliminate that. And so you didn't sort of grow it completely before you projected it down. Okay? So you could say, why did you teach us about factors? Why was there a factor zoo? Why are there database joins? Why don't we just write algebraic expressions like this and move the summation around according to the laws of algebra and probability? You can do that if you want. In fact, some people teach it that way. Enough said. Okay. So let's do marginalizing early. Okay, at this point, don't even track the individual numbers, though. Feel free to go back and actually go through these slides your own. We're now, instead of going to join, RTL, marginalize, let's just sort of marginalize aggressively, okay? So we're going to join on R. Boom. The R and T nodes become one big factor, R comma T, okay? So these two factors get consumed to produce their join. But now we can sum out R because we don't care about it, and it only appears in one factor. See, this was too early here to marginalize it, okay? So we sum out R. Boom. R comma T is just T, and this factor just got exponentially smaller. Okay, got half as big. Okay. All right, now we can join on T. We get something two-dimensional over T and L. but then we sum out t, and it's back down to L. Is this better? Yeah, it is actually better, because when we did join, we got the big three-dimensional thing, and here it never got that out of hand. We never got anything bigger than two-dimensional in this order of variable elimination. Okay, so let's take a break, and then we'll present kind of how that works with evidence. We'll do some examples. We'll talk about why all this stuff is NP-hard anyway, and the difference between good and bad variable orderings. Okay. All right, 2 minutes. Perfect. All right. Okay, let's get started again. So what about evidence? What are we doing here? We're looking at the variable elimination algorithm, which is an algorithm for computing queries in a Bayes net. And so far, we sort of have some pieces, but we don't quite have an algorithm. Like, we haven't really said what the inputs and outputs are. We've just said what the building blocks are. The building blocks are joining, where you gather all your factors that share a specific variable. And then, after you join them, that variable will appear once in one factor, and it turns out it'll appear on the left side of the conditioning bar, and so you can marginalize it out. So, in order to actually have the full algorithm, we need to talk about what happens with evidence, what happens with your query, what are the inputs, what are the sequences, what are the choice points. So we're going to do that now. So, your inputs are, you have a bunch of local factors. They're the conditional probabilities that come with your Bayes net. There's no evidence yet, but you know which variables have specific values because they've been observed. Like, maybe you've observed that the patient has this temperature. So now that random variable is evidence. So what do? So you start with your factors. So if you have no evidence in this running example of P of R, P of T given R, and P of L given T, these are the conditional probabilities that come with your Bayes net, no observations. But if I'd like to compute what's the probability that I'm late given that it's raining, my initial factors change. P of R changes because the minus R part is gone. You say, I only saved one line. But remember, you've conceptually just knocked out half your joint distribution. So that's great. You've just knocked it out locally. And then T given R becomes T given plus R. So it's still probabilities of T given R. except now instead of being a two-dimensional object, it's a one-dimensional object. And P of L given T doesn't change because it doesn't mention R, which is our evidence. So you start with the same factors as before, but everywhere your evidence appears, you delete all of the rows that correspond to the values other than the observed evidence. All right, so you eliminate, and now what you do is you eliminate all variables. Not going to eliminate the evidence. We already took it into account. We're happy. The evidence is happy. We don't need to eliminate it. We don't need to join it. Okay? And we're not going to eliminate or join our query just yet because that's what we want to have left in the end. So what we're going to do is we're going to go to every other variable that isn't our evidence. Here our evidences are. And here our query is L. So we're going to go to all the others, which is just T, and we're going to eliminate them. What does eliminate mean? Join and marginalize. Okay. So if we do that, and we'll do an example in a second, what you'll end up with is you will end up, if you do probability of late given R, so meaning you select all of the plus R rows, and then you find everything like T that isn't mentioned in your evidence and query, and you join and marginalize, you'll end up with one factor at the end, so there'll be a join at the end, and at the join at the end, you'll end up with one factor that looks like this. It'll be a selected joint of the evidence in the query. So the evidence has one value, and the query has all its values. So it has plus L and minus L, but just plus R because that's your evidence. As a data structure, that's a one-dimensional object. As a semantic object, those are all joint probabilities of R and L. So if I normalize that, meaning divide it by its sum, I'll end up with a probability distribution over L. There's an entry for every value of L, and it sums to 1, so it's a probability distribution. Moreover, it'll be the conditional probability of the query variable given the evidence. Okay? So let's do some examples. That's it. We're going to do the general. We're going to say what it is in general, and then we're going to do some examples. Your query, it has a query variable. You can actually have multiple query variables, but for now we'll pretend there's just one. There's evidence. Okay. You can have anywhere from 0 to everything else in the network as evidence. Your initial state is the local conditional probabilities instantiated by the evidence. Okay? While there are variables which are neither E variables nor Q, pick a hidden variable, join everything mentioning H, and then sum out H. So you join on H, you sum on H. Once that's done and you can find no more hidden variables, what's left in your factors? All the hidden variables are gone. What's going to be left is Q, which will appear as a vector, and a bunch of evidence values, which will not appear sort of as axes. Countdown to goodness. I think we can wait an hour for the goodness. Okay. All right. So the last thing you're going to do is you're going to join all your remaining factors and normalize. So you select your evidence, you hunt down the hidden variables in order of your choosing, and then at the end you join and normalize. Okay. Here's an example. All right. There's going to be a lot of little conditional probabilities with conditioning bars and some capitals and some lowercase. Just try to track the flow of how these objects are sort of changing algebraically. So at the beginning, here's my alarm network. So forget variable elimination, forget my query. There's my network. That means we're going to have a model here over A, B, E, J, and M. Okay, great. And that means in principle, there is a joint probability over A, B, E, J, and M, but we're going to try our very best to not actually assemble that five-dimensional object. Somebody comes along and says, hey, I want the probability of burglary given that John and Mary are both calling, let's say. So let's pretend those are plus J and plus M. Okay, they're just written as J and M. Pretend they're plus. All right. So I say, all right, let's do it. Well, what I'm really going to do is calculate this joint probability instead. It's the same thing, but unnormalized, and then I'll normalize as a last step. So let's calculate it. Well, rather than actually going through and introducing variables and summing and trying to do this sort of arithmetically, we're going to do variable elimination. So here we are with our 5 factors. Each one corresponds to a node. So for example, this J node has probability of J given A, and it's been instantiated to select to match the evidence. So I start with 5. P of B, P of E, those are the 2 top nodes. P of A given B comma E, that's the big node in the middle. It's already a 3-dimensional object, so that one might be trouble. And then I've got J given A, but it's already been selected to the value of J plus that I have, and M given A has also been selected. These are, remember we talked about them, they're selected families. They are not probability distributions over A. They're conditional probabilities over plus j, one for every value of a. What do they sum to? Who knows? Okay? All right, so here are my 5 factors, which are my original conditional probabilities from the Bayes net instantiated by the evidence. So I pick variables in some order. Let's pick A. So I choose A. I summon together all the factors that mention A, of which there are 3. All right, so I got to join all these factors together. What am I going to end up with? Well, whatever I end up with, it's going to involve A and B and E, and actually also J and M in terms of what it means, but they're not, as a data structure, they're not axes here. These are going to be 3-dimensional objects. So I'm going to have something that's going to be a factor over A, B, and E, and what it's going to correspond to is a bunch of products of P of A given B, E values times P of J given A values times P of M given A values. What's that? That's going to be the probability of A and J and M given B of E. So if I put all those things together, you say, how did I know that? Well, that's the only thing they could be. You sort of union up everything that's on the left of the conditioning bars, and then whatever's left is on the right of the conditioning bar. Okay? All right, so I'm going to join them up, and then I'm going to sum out A. I joined on A, and now I'm going to sum it out, and I'm going to end up with a table that represents joint probabilities of J and M given B and E. Except J and M have single values, which means how big a data structure is this? Dimension 1, dimension 2. Okay, there's going to be a 2-dimensional array for values of B and for values of E. And for every entry for a B and an E, it'll give you the probability of J and M given that B and E. Okay. Well, here we are. We got factors again. I dispose of these. They will confuse me, so I throw them out. Besides, I don't need them anymore. I already have their replacement. So now I've got P of B because it was not harmed in that joining. I've got P of E, it was not harmed in that joining. And these 3 here have been replaced by this one. Okay? Almost done. I want P of B given J and M. There's one more hidden variable, which is E. So I'm going to join and eliminate. So I say I will pick E. When I pick E, there are 2 factors that mention E. The original P of E and this new thing that I just made that has E as one of the conditioning properties. When I join these things together, I'm going to get another 2-dimensional object. You'll see E has moved from one side to the other because I multiplied by a P of E. And then no sooner does it move than I eliminate it, and I end up with the probability of plus J plus M given B. So there's going to be a value for plus B and a value for minus B. Now I've got 2 factors left. I've got the original P of B, and I've got this new P of J, comma M given B. All right. I'm all out of hidden variables. My evidence variables were taken into account when I instantiated them. All that's left is my query variable. I could join and eliminate one more time, but that would be silly because actually I don't want to eliminate B. So what I'll do is join but not eliminate. So the last thing I do is a big join. I join everything that's left, and I will end up with the probability of my evidence jointly with my query variable. And because this is a vector, there's one value of this for plus B and one value for minus B. And if I normalize that, I will get the conditional probability of B given that evidence. And I'm done. Okay, so that's how the variable elimination flows. You start with a bunch of little factors, you join. And when you join, you might grab 7 things and build some mega factor, and then you eliminate one thing. And so you have to choose wisely about what you join, because for bad orders, you might build things faster than you're shrinking them. Okay? All right. Do not process the slide. Don't do it. This slide is simply saying that instead of working with these factors, I could have worked all that out using products and sums and laws of distribution and all of that. Okay, variable elimination is a mechanical way of figuring out how this is going to work in a way that's much easier to reason about than these sort of algebraic arithmetic expressions. Okay, but feel free to eyeball this later and see how it's doing the same thing. But don't eyeball it now. I'm going to make it go away. It's gone. Oh man. Okay. All right. So, variable elimination. Somebody hands you a network. And in that network, there is a whole bunch of variables that are maybe observed. So, observe, 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 observe. Maybe I observe all the y's. This is pretty common, right? You've got some underlying cause you'd like to infer something about, and you see a bunch of distal effects, and you want to do a diagnostic inference here. And so I'd like to know what's the probability of something given the rest. Maybe I want to know what's the probability of xn given all those y's. Okay. Now, first of all, let's just figure out what's going on. These guys, these are the evidence. Okay, so those are the evidence variables E. The y's are the e's. The query variable is x sub n. Everything else, z, x1, x7, all that stuff, that's all hidden variables. So the evidence, I'm going to instantiate that. Fine. We're not going to eliminate the y's. The last thing left standing is going to be xn, and we'll join and normalize on that in the end. And in between, all this other stuff, let's put a green box. All the stuff in the green box is hidden variables. These are the h's. And these need to get eliminated. So we have an algorithm. We're going to point to one, we're going to summon its factors, and then we're going to multiply them together and then marginalize out over that axis. So let's actually try something. Let's try two possible worlds here. One is where we eliminate x1. Let's just do it real quick. So we're going to summon all the factors that involve x1. Well, there's this p of y1. That's evidence, so it's going to be a lowercase y1 given capital X1. Okay, that's cool. What else mentions x1? What other factors in this network have an x1 in them? There's only one more. There's the one living under p of x1. So it's going to be p of x1 given z, given its parent. Okay, so we're going to join them. So let's do it. We're going to do a join on these things. We're going to end up with some new data structure. It's going to contain probability of little y1 and big x1. So it's going to be a given z. It's going to be, as a data structure, two dimensionals. There's a dimension for x and a dimension for z. And every entry is a probability of y1 given y1 and x1 given z. Now, so that's the join. And now we're going to marginalize out over x1, and we're going to end up with probability of y1 given z. That's okay. No harm done. And then I'll do it for x2 and for x3. That'll be okay, right? Let's think about another path we could take. So this is where we pick x1 as our first variable to eliminate. So now let's eliminate z. Eliminate z. Okay, let's see what happens. Step one, we're going to summon every factor that mentions z. Let's figure out what factors mention z. Well, there's p of z, that mentions z. That lives in here. All right, what other factors mention z in this Bayes net? Let's think about which nodes either are z, we got that one, or have a parent that is z. Well, p of x1 given z, that's one of them. What else? P of x2 given z, p of x3 given z, p of xn minus 1 given z. All right, do you have a bad feeling? I have a bad feeling. So we're going to take all these things and we're going to join them together. What do we get? We're going to get a monster array, right? This is going to be something which is going to be it's going to be some factor over x1 all the way through xn minus 1. Actually, it's going to be all those product together, p of z, then we're going to eliminate z. Let me just... Let's do it this way. Okay, so we're going to form this joint probability, and then we're going to eliminate z. All right, what are we left with when we eliminate z? We're left with a giant factor over all of its children. That's kind of bad, right? We just built something exponential. Sorry. Okay, that was a bad choice. We should not eliminate z. Why? Intuitively, what's going on here? In this network, you've got z, which is a cause. And there's a whole bunch of things which are independent given z. What happens if we eliminate z? They're not independent anymore. Suddenly they all kind of rise and fall together, but it's not mediated by z anymore because we just nuked z. So what's left is a big joint factor over everything that's left that has now been coupled. So we have to be very careful when we do variable elimination that we don't pick variables early on that cause everything left to couple, because that's going to end up with exponentially large things right away. So there are good variable orderings and there's bad variable orderings. Is there always a good ordering? No. This is NP hard. How hard is it to find the best ordering? NP hard, right? So, however, good luck. Good luck finding a good ordering. Okay. So, this can be exponentially better if you pick a good ordering. Can't always find a good ordering, but you can try. Okay? So the ordering affects efficiency. Okay. We have an algorithm, variable elimination. You join things and eliminate immediately. Some orders are better than others. Finding the best ordering can be hard. The computational and space complexity of this algorithm is going to be determined by how big these things that you build are. If you just build up the whole joint probability, it's going to be bad news. So it's going to be determined by how quickly you let those factors grow. The elimination ordering can be they can vary greatly how big that factor is going to end up being and therefore how expensive this is going to be. So in the previous slide, there was an exponential difference. All right, so we already knew this. Is there always an ordering that results in only small factors? No. Can you find the best ordering? No. Any questions on that before I show you why? Okay. In practice, often there are reasonably good orderings that are reasonably easy to find, and everything ends up being quite efficient. But as always in AI, the worst case is very, very bad news. The reason the worst case here, if you think about it, we can actually go directly to thinking about a CSP and in particular a satisfiability problem. So how could I use a Bayes net to solve a satisfiability problem? If a Bayes net can knock out the solution to any satisfiability problem efficiently, then we just found a way to solve SAT efficiently. We don't think that's possible, and so therefore we know that we've got sort of bad news with these Bayes net problems in general, because even though they might not encode satisfiability, they might, or something else equally bad. So here's how you could, given a satisfiability problem, build a Bayes net. So somebody drops on you a satisfiability problem. What do those look like? They are a bunch of variables, and then you have a bunch of disjunctions, ORs, of those variables or their negations. And then those little clauses are all ANDed together. How could I write that as a Bayes net? Well, variables, x1, it's either true or false, and I could stick that in my network, maybe with a distribution that says 50-50 true or false. And here's x2, 50-50 true or false. And then each of these clauses is going to say, well, what's y1? Well, guess what? This is y1. y1. Okay, what is y1? y1 is true if x1 is true or x2 is true or not x3 is true. How do I encode that? Well, remember, hidden inside this Bayes net for y1 is the probability of y1 given various assignments. And so you just set it up so that y1 is false if I have a bad configuration of x1, x2, and x3, and y1 is true otherwise. So I can do that for y2 and y3, and then each of the variables, these are the variables, this row is the clauses. What's this structure? This structure is going to be the ands. This is the thing that's going to say all of those y's have to be true. Okay, and you similarly fill in their probabilities so that they enforce they're true only if both of their parents are true. Then you go and you say, hey, what's the probability of z? Well, if there's some way to assign those x1s so that everything percolates down to true, then the probability of z won't be 0. And if there isn't, it will be 0. And so by looking at this marginal probability, you can answer whether or not this thing is satisfiable. And so you say, that's a weird sort of construction. Why is there this tree-shaped object? Why don't we have variables, disjuncts, conjuncts? Okay, let's do it. So let's say instead, all those y1 through yn went straight to a z. Well, they'd have to all be parents of the z. Like this. And if z has a ton of parents, what's living in there? Well, it's something that says all the parents have to be true. And like exponentially many other things, because you don't want to have a lot of parents. So this is a construction that's designed to stay compact while specifying that conjunction. If you made everything a parent of z, it wouldn't be compact. And so it's not actually that bad that it takes a long time to solve because it's a big thing. So in general, for these reductions, you need to have something small that is hard. This keeps it small. All right, we now know Bayes net inference is NP hard. There's no way around that, but in practice, often things are not that bad. So let me give you some examples of things that aren't that bad that maybe will remind you of things you've seen in CSPs. So one thing that's not that bad is, well, before we talk about polytrees, one thing that's not that bad is a Bayes net that's a chain like this. Okay, why is that not so bad? Well, if I have to do variable elimination on this, it turns out that if I sort of eliminate them from left to right, nothing will really explode in size. Okay, really, the thing that's bad news is when you have lots of things that get coupled together. So a parent with a lot of children, and you eliminate that. Here, there are things don't have that many parents, don't have that many children. Okay, in general, a polytree is something that is a directed graph that does not have undirected cycles. You can think about it basically as a tree. But there are some other cases like two parents pointing at the same node. For polytrees, you can always find an efficient ordering. And in fact, that example we saw with the z's and the y's and the x's, not the satisfiability one, but the one with z on the top, that's an example of a polytree. And for polytrees, there can be bad orderings, but there's always a good one. So what does that remind us like from CSPs? Remember, for CSPs, if you try to do your backtracking search, that might be expensive, but if you arrange things just right, then you could be greedy if you did this sort of message passing algorithm for constraint for enforcing arc consistency. This is a very similar thing. They're very deeply related, in fact. And there's also notions like cut-set conditioning. So just like in a CSP, if you don't have a polytree, but if a couple nodes would go away, you can do the same thing here. You can sort of instantiate the problematic nodes in all the different ways, which creates a number of subproblems that's exponential in the size of the cut set. But if what's left is a polytree, then you have an efficient algorithm over what's left. So you can see the sort of same idea from before. Take a CSP, find a cut set that leaves a tree-shaped residual, and now everything's efficient. You can do the same thing here. Take a Bayes net, find a relatively small set of things that leave a polytree residual. You have to work out what residual means here, and then you do something efficient on what's left. Okay? So you can think about the specifics there. All right, what do we have? We talked about representation. What is a Bayes net? What joint probability model does it represent? We talked about conditional independence. What can you conclude about which variables do and do not influence each other given other evidence? We talked about various things in probabilistic inference. How to do it exactly in exponential time by enumeration. How to do it exactly in exponential time, but often faster with variable elimination. We talked about why this thing is NP hard. Next time we're going to talk about sampling, which is a way of doing inference really, really fast and maybe getting the wrong answer, which is another way of attacking these problems. So we'll talk about sampling next time and then get to learning later in the course. All right, we'll stop there. Thank you.